and welcome. This video is made up of two parts. First, we demonstrate the use of our T.L.U.D stove, then we speak to some of the economic and environmental paths that biochar offers. Biochar is charred biomass, a type of charcoal that can be charged with nutrients and microbes. Added to the soil, it can persist potentially for thousands of years, acting as a beneficial amendment and buffer. The process of making biochar, called pyrolysis, releases about 2/3 of the heat stored in this biomass. Instead of being discharged to the air as heat pollution, this can be easily and safely used for heating spaces, water, and cooking. The remaining 1/3 of the heat is chemically bound up in the biochar. During the COVID quarantine, Bill Knaus conceived of and experimented with the stove model shown in this video. He had no access to the fabrication tools normally relied on. The goal was to design a top-lit, updraft stove, or T.L.U.D, that was much cheaper and easier to build with fewer tools than the earlier models. The result is a new design, built at less than half the cost, with increased performance when it comes to making biochar and providing heat. This is the heat exchanger. The tube is 24 by 8 inches in diameter. The fabric you see in the bottom here is refractory insulation, which keeps the temperature of the flame optimal where it comes into contact with the steel of the exchanger. The heat exchanger sits on a welded frame made of 1/2-inch square steel tube. Heat exchangers can be made in different sizes and mounted in the home to fit the needs of the people using the T.L.U.D stove. Here we have the controller box. The panel on the left has switches for power and reset, 12 to 15 volt DC power input, a fan speed control knob with LCD display, and a thermostat with dial. The 8-inch circle around the opening is fireproof rope, which forms a gasket between the control box and burn chamber. The control box of the biochar heater is constructed from cement board 3/8 of an inch thick. The box is roughly 16 by 12 by 3 inches. In this latest version, we have mounted rollerblade wheels to make loading safer and easier. The controller uses a thermostat which shuts the unit off when it has finished burning. This also triggers a buzzer that is silenced with a switch, resetting the circuit. The small knob allows the user to increase or decrease the fan speed, which allows for some changes to be made in burn time and intensity. This bucket has been pre-filled with a full load from the 8-inch burn chamber that we are using. The load we are demonstrating today weighs 14 pounds, 8 ounces, or 6.5 kilograms. The finished biochar, seen here, weighs 3.5 pounds, or 1.5 kilograms, meaning that around 25% of the biomass has been left over to be charged and stored in the soil. Our T.L.U.D stove is capable of burning different types of dry organic materials, many of which are the byproducts of farming, forestry, or thinning. In this demonstration, we burn pecan shells. The shells are a cheap and often available fuel source in the southwest United States. The moisture level is very important. The fuel should be as dry as possible. Here, Jamie demonstrates the superior balance one can cultivate through practicing biochar-based heating. This is known as stork form. Or maybe the producer cluttered the set. In this video, we are plugging the unit into a 12-volt 3-amp wall transformer. One can also use a rechargeable battery pack as seen here. Any matching DC power source can be used. The fan and control circuit are very simple with low power requirements. The control box has been started, so the fan is running. The air is flowing up through the holes in the base of the burn chamber. Next, we use some lighting fluid to start the burn. Our T.L.U.D averages a full burn in 2 hours, in which time 75,000 BTUs will be generated, at 5,000 BTU per pound from our pecan shells used here. Here we show the top of the heat exchanger. The cleanliness of the exhaust indicates a complete combustion. Looking down into the flame in the chamber, and we get a good view of the gases igniting. As a teaser, we thought we could show a little of what we had for lunch during the shoot. Cooking with T.L.U.Ds is straightforward and easy, making your next barbecue or camping trip all that more ecologically friendly. Here, you can see the unit is finished running. We take and carefully pour the charcoal into an airtight metal container so that combustion comes to a stop. We also have caps for the burn chambers, allowing the hot chamber to be placed outside to cool before emptying. With multiple burn chambers, you can continually run the T.L.U.D stove as needed. For the next part, we would like to speak to the economics and climate change implications of using biochar. Our experience is from work in the southwest of New Mexico, in the United States, and in Palomas, Mexico. For over 7 years, we have been producing heat for a few poor Mexican families, while producing about a ton of biochar per year per family. The biochar is used to improve the soil in community and kitchen gardens. With information from this background, and using conservative estimates, we would like to share some of the economics and potential directions for a path to achievable carbon capture and storage and avoided emissions for the world. The basic facts of biochar that are important as related to this presentation are: number 1, when 1 ton of biochar is incorporated in the soil, it stores around 3 tons of the CO2 that was removed from the air by the tree. 2, when biochar stove fuel is from a waste stream, we can stop using fossil fuels, permanently avoiding another 3 tons of carbon dioxide emissions. 3, around 4 tons of pecan shells produces a ton of biochar. In Palomas, Mexico, the only commonly available heating fuel is propane. $1,200 worth will produce the same amount of heat as you get when you produce a ton of biochar. The pecan shells for producing a ton of biochar cost $100 or more delivered to the area. The wholesale value of biochar just across the border in the United States is around $1,000 a ton for bulk quantities. Retail packages of biochar sell for nearly $4 a pound. Adding these numbers up, we find that producing 1 ton of biochar saves $1,200 in propane, makes between $1,000 to $8,000 worth of biochar, and removes or avoids 6 tons of CO2 emissions, a three-pointer worthy of the attention of anyone interested in addressing climate change. The good news is that there are 3 billion people, primarily in the global south, that rely on biomass for some or all of their household energy needs. To engage these 3 billion people in producing biochar, there should exist a globally accessible voluntary carbon market, specifically for carbon dioxide captured and stored by households engaged in producing biochar. The trending price on existing voluntary carbon markets for biochar permanently stored in the soil is $100 a ton. These markets are not accessible to small producers like our Mexican families. In addition, the Biden administration is reportedly on course to set a social cost of $125 per ton, with the price expected to continue rising rapidly. Thus, the low end for the voluntary carbon market is around $100 per ton. For 1 ton of biochar, you would be either removing and storing or permanently avoiding the emissions of around 6 tons of CO2. The only other reported efforts to remove CO2 directly from the air and permanently store it is by Climeworks and similar startups. In September of 2021, Climeworks started operating the world's first direct air CO2 capture and storage, or DAC plant, in Iceland. Climeworks will be removing 4,000 tons of CO2 per year, which they are selling as offsets for $600 per ton. This is only made possible by Iceland's abundant supply of geothermal energy and favorable geology for deep underground storage. Without these advantages, the price is expected to be around $1,100 per ton. Nevertheless, Climeworks will be removing and permanently storing 3 seconds worth of the worldwide yearly anthropogenic or human-generated carbon dioxide emissions in their Iceland plant every year. As a comparison, there was a voluntary carbon market for CO2 removed by households, a carbon market which priced biochar between the current market highs and lows. Our Palomas, Mexico project could quickly expand the use of our simple T.L.U.D stoves. We could accomplish the same amount of CO2 storage as Climeworks achieves per year with 700 families. Unfortunately, we do not yet have a voluntary carbon market for CO2 emissions avoided or removed by households. Furthermore, the supply of pecan shells is limited or non-existent in most locations. But there are many people, especially in the United States, that are interested in making biochar for their own use, or even for the heat from a very affordable T.L.U.D stove. With that in mind, we should briefly look at the economics of using commercially available pellet fuel to make biochar for use at home. The retail value of biochar is around $4 a pound. At current pellet prices, the biochar will cost between 20 and 27 cents a pound, $400 to $530 a ton when adjusted for the value of the heat produced. The heat produced on one 5-hour burn in our stove is 125,000 BTUs, with 25% of the biomass left over as biochar. In conclusion, we have come to believe that biochar is the lowest cost, most widely available method in the world to quickly sequester carbon dioxide at scale. Our compulsion is to align this opportunity to simultaneously address economic and social disparity between the global South and North. We hope you will consider the case we are making and join us in whatever capacity you can.